Finish up 6, 7 first, finish up the physical applications. And the last physical application has to do with force and pressure. And the main application here is that we're imagining water pressing and exerting a force on a window in a pool or on a dam or whatever it is. And we want to figure out that cumulative force so that we can build our window or our dam strong enough that it's not going to collapse. So last class we talked a little bit about this hydrostatic pressure. Water is pressing in all directions simultaneously. And the one consequence of that is that if we have a dam, it doesn't matter how much water is behind it. We come over here, the water is pushing that way, and this water is pushing that way, and it kind of cancels each other out. So whether we have 1 foot behind the dam or 100 feet, the force on the dam wall is the same. So that's our big takeaway from hydrostatic pressure. The idea with the units is going to be kind of important here. We are going to be finding force on a wall, and so the simplest way to think about force is that it's pressure times area. All right, so pressure times area is going to, if we multiply pressure times area, we will get force. And if we go back to the slide up here where we started with rope, at the very top of that slide, I've got all the units broken down. And if you look down at this lower section, force is going to be pressure times area, ADD, so that acceleration, density, depth piece, the ADD part, that is going to have units of pressure, and then of course area and area match. So here are the units broken out where I took acceleration, I took density, I took depth, they're all there. And it turns into, if you put all those units together, you end up with a kilogram times a meter divided by a second squared. That's force. Kilogram meter divided by second squared is force, which is a Newton. So the units, if you look at that slide, just if you're not 100% comfortable with the units, come through here and just play with them and make sure that they line up with what you're thinking they should be. And make sure you kind of are comfortable enough with them. So our basic idea then is that to find force, instead of ADD volume, we're going to have ADD area. So remember that when we were doing work, we had ADD volume. And the only difference is 1 unit of length. If we take area and multiply by 1 more unit of length, we get volume. And if we take force and multiply it by distance, we get work. So if we were to multiply both sides of these by distance, we'd end up with work on both sides. So force, we just turned the volume into an area and we now have force. And again, the cool thing about hydrostatic pressure is that it doesn't matter how much water is behind the dam, the force is the same. So build it as far back as you can. Okay. Now, just like with volume, the volume was an elemental volume. In other words, we were getting the volume of a slice. So we had that dy piece, so we had a very thin slice. So we weren't talking about volume of the tank, we were talking about volume of a slice. The same idea here, this area is an elemental area. And when we look over at our picture here, this is the area that we're talking about right there. We're talking about the area of an elemental strip. So with volume, we're taking cross sections that give us circles or rectangles or whatever, and then we add a thickness to get a slice. Here, we're only dealing with 2 dimensions. We're not dealing with 3 dimensions anymore. We're talking about the force on this wall. So when we look at this little strip here, the idea is that we take a horizontal strip where we have constant pressure. Right? Pressure is constant right there. And then we add some thickness to it to create area. If we just take a thin line across, there's no area, but then if we multiply by dy, then we have a strip. So the area of this strip will be whatever the width is multiplied by dy. That's the area of the strip. So when we come down here, what we are going to see is this piece right there. There is the area of the strip. The area of the strip is the width of the strip multiplied by, before we do the limit of the Riemann sum, we call it delta y. Once we take the limit of the Riemann sum, the delta y becomes a dy. So there's the area of the strip. And then pressure is going to be the ADD, acceleration density depth. That will give us pressure. And again, units are right there. So let's go ahead and do one of these and see that it's really not too different from what we did when we found work. So here is the integral written out in sort of more incomprehensible language. Writing it like that, super simple. ADD area, area of strip, not area of wall. So let's try it. So we start out with the integral. And we are dealing here with a trapezoidal wall. Again, it's 2 dimensions. The water's pressing on this. And we want to figure out that cumulative force on that wall. And so just go through and fill in our acronym. So A, D, we're dealing with water. We've seen that the density of water is 1,000 kilograms per meter cubed, density of water. And then distance. Okay, let's make sure we understand that. So I'm drawing a width here. So that goes all the way across. That's one-dimensional right now. If we multiply by dy, then it becomes area. It becomes a strip. And this d is interpreted almost identically to what we did with the troughs and the vessels. It was the distance that that cross-section had to travel if we were pumping. The only change here is that that cross-section is not traveling, but it's how deep it is. So it's the distance below the surface of the water. So it still is calculated in the same exact way. If this full distance is 15 meters and we put this little cross-section right there, this integration element right there, how far is that integration element below the surface of the water?
15 minus y.
15 minus y, exactly. So we calculate that second d in the exact same way. It's whatever that full height is minus y. So that is going to be our second d. So far we've done nothing different than what we did with the work problems. So there's the ADD. This is also pressure. ADD is pressure. So that will have units of pressure, pascals if you want to use that unit, you can. What about limits of integration here? So when we add this, what do you think our limits of integration will be? So if we add the little thickness here, the thickness there is the dy. What do you think the limits are going to go from?
0 to 15.
0 to 15. We have cross-sectional strips from 0 all the way up to 15. So the limits of integration, we'll calculate them and think of them very similar to what we did with the work problems. So now here is the only difference. Instead of an elemental volume, we have an elemental area, and the area is just W multiplied by dy. So that's what's going to go in right here, W multiplied by dy. This is the area that we are speaking of. So we need to figure out what W is. That's going to be the hardest part usually. So what we are going to do is imagine a coordinate system right here. So if we put a coordinate system like that, we are going to need the equation of this line over here. And so the equation of a line is best found by using the point-slope formula with a pair of points. Well, to get this pair of points, if it's 10 meters all the way across there and we put our coordinate system like that, this point will have what coordinates?
0, 5.
So 0 will be the y coordinate. 5 would be the x coordinate, so 5, 0. And how about the ordered pair for that coordinate up there, that point up there? This is
15.
So it's 20 all the way across the top, so half the top is 10, and then the height of this trapezoidal wall is 15. So now we have our 2 points, and to get the equation of the line, we use the point slope formula. Y minus y1 is equal to m times x minus x1. The point that we choose, the coordinates that we choose, it doesn't matter if we use that for the point. You could use the top point also. It does not matter. Point slope formula, doesn't matter what point you choose, just any old point. I will always choose the one with a 0 because it's easier. So this will be y minus 0 equals the slope. Okay, slope. We've got 2 points, rise over run. So if we go up, we're going up 15 and over how many? 5. So up 15 over 5, slope of 3. And then x minus 5. So that is the equation of the line presented as a y value. Right now this function is measuring height. How do we want this? What do we want this function to measure, though? Vertical or horizontal distance?
Horizontal.
Horizontal. We're trying to find this width, the W. We want to measure sideways, so we have to isolate the x. So this function right now is measuring height. It's measuring distance above the x-axis. If we solve for x, it will be measuring distance from the y-axis. So we'll add the 15, we'll divide by 3. So now it's measuring horizontally from the y-axis over. Whatever y value you put in, it will tell us how far we are to the right of that y-axis. Okay? So 1/3 y plus 5. That is measuring that distance right there. That is what that x is measuring. So how do we get to W? Multiply by 2. That's half of W. So we're going to come up here. Let's just pull the 9800 out in front. That always seems to be part of these problems. We have a 15 minus y. And then we have to double the x. So W is 2 times 1/3 y plus 5. Multiplied by dy. So there is our setup. Let's pull out the 2. Maybe we'll multiply that out later. So inside here, the 2 factors that are left, we've got that and that. There's a couple of things we could do. We could try to be clever and factor out that 3 in the denominator just so that we're not dealing with fractions. We don't have to, but that might be easier. Question?
Where did your 2 come from?
This function here is only measuring half of W, right? When we solve this, if we have the equation of this line and we isolate x, it's now measuring only from here over to here.
Okay.
So we need to double that to get all the way across that trapezoidal face.
Okay. So that's all our W.
Exactly. So W goes all the way across. We isolate x here. That's only going halfway across. So that is to create all of W. So W is going to be this whole thing right there. So let's factor out the 1/3 just to do a little bit of algebra practice. You don't have to, but it's nice not to deal with fractions when we FOIL those 2 quantities together. So let's see if we can factor out the 3 properly. So factoring out the 3, we have 15 minus y. I factored out the 2. Factoring out this 3 in the denominator, I'm factoring it out of this quantity right there. So if I factor out that third, that 3 is in the bottom, we're left with y. What would this constant be? What would be added to y if we factor out a 3 in the denominator from that 5? 15. Because there is no 3 here, so you can imagine multiplying by 3 over 3, and then you're factoring out this 3, so there's still a 3 left in the top, so that would turn this into a 15. So that is a good skill to be able to factor out that fraction, and now it's a lot simpler looking for when we FOIL. All right, so let's just leave these constants alone for the moment. Let's do our FOILing and see if we can get somewhere nicer. We're going to do it in descending order. Minus y squared. Oh, we see that there's cancellation, right? There's going to be a negative 15y and a positive 15y, so those cancel, and we'll end up with just these two terms. And the integration will then be minus y cubed divided by 3 plus 225 multiplied by y from 0 to 15. Let's see if any of these constants out here cancel with what we have in there. Plugging in the 0 gives us no force. We're finding force. There's no force there. Plugging in the 15. All right, so 15 times 15 is 225. And then we have to multiply by 15 again. So this is going to be minus 15 cubed over 3 plus 15 cubed. All right, 225 times 15 is 15 cubed. It's 15 times 15 times 15. So what I'm going to do is factor out that 15 cubed. And what will be left when we factor out the 15 cubed?
1/3 plus 1.
Negative 1/3 plus 1, so 2/3. Well, 1 minus a third. So 2/3. And now we just have to multiply all that stuff together, and we will get our newtons, our total newtons on the wall. I don't see a lot of cancellation there. I see that we could simplify this 15. There's a 3 that would go into one of them. There's a 3 that would go into another one of them. So if we're just doing it by hand, this is what I would end up with. One of the 15s sticks, and 2 of the other 15s turn into 5s. And I guess I would turn that 2 into a 4. So if somebody wants to multiply all that together, tell us how many newtons we get. A lot of newtons. Tons of newtons.
14,700,000 newtons.
14,700,000?
Yes.
A lot of newtons. So that's the force on the wall. All right, any piece of the setup there? Let's try another one then. These they're not that different than the work ones. We have the same kind of shapes. Let's try a triangular one. So here, same context. We've got this wall. There's going to be water pressing on it, and we want to know the total force on it. So once again, our integral that we set up, in order to find this force, we are going to do an ADD times area. And area is going to be the width of this strip here, the width of this integration element, multiplied by dy. So In your mind, you can imagine it as a strip, and then the thickness of the strip is dy. And so that area that's in that integral is just w multiplied by dy. So this is at a random y value right here. And let's fill in some of these blanks. Limits of integration.
0 to 30.
So 0 to 30. We're going to have strips all the way across from 0 to 30. And then we do our standard stuff, 9.8 times 1,000. So acceleration, density, 1,000 kilograms per meter cubed. And then d, distance. How about distance?
30 minus y.
30 minus y. So upper height is 30, and we're going to subtract off the height of that horizontal element. And now area. Again, not area of the triangle, it's area of this rectangle right here. That's what we're trying to find the area of, that rectangle. Well, we know that the height of that rectangle is dy, if we think of that direction as height, dy, and then the width of it. So all we need to do then is figure out this w. This is always the hardest part when we're doing force, is finding that distance across. So we're going to set it up very similar to what we did before. We're going to create a coordinate system. And this one's going to be a little bit easier because when we look at our 2 points, one of them's the origin. We know the coordinates there are 0, 0. And the other one is right there. This is going to be a y equals mx plus 0. So all we need to know is the slope, really, because it's y equals mx. What are the coordinates of that point up top?
10, 30.
So halfway up here is going to give us 10 across, and then 30 all the way up. 100%, 10 comma 30, that is our point. So the slope then, we go up 30 over 10, so the slope is 3. So y is equal to 3x. That is the equation of the right edge of this triangle. But do we want it presented as a y value? Are we trying to measure height? No. We're trying to measure height sideways. We're trying to measure this distance across. So x will be 1/3 of y. So that's going to be measuring over to here. So halfway. When we isolate x, x is measuring the distance from the y-axis to the right. That's only half of our strip. So what are we going to do to that x? Double it, multiply by 2. That's all we have to do. So our next step here, we'll have our 9800, 0 to 30. We'll have 30 minus y. And then 1/3 y. And we have to double it. So this part, all that right there is w. That is going to give us 9800 on the outside, 0 to 30. All we have to do is distribute this. We could factor out the 2/3 all the way to the front. Let's go ahead and do that. That seems like a good move. So 2/3 all the way to the front. So I'm factoring out this third and that 2. That's factoring out to the front. So we'll be left on the inside with 30 times y minus y times y. Like that. So 2/3. Oh, I just realized that. Does 3 go into 9800?
No. No.
No? So what do you do 9800 divided by 3?
He's like, I'm sure.
9 plus 8 is 17.
And 1 plus 7 is?
8.
Oh, 8's not divisible by 3. Ah, yeah, never mind. For a second there, I was thinking that we were getting, that when we added, I was thinking that 7 plus 1 was, never mind. 7 plus 1 is not divisible by 3. Never mind. I was like, shouldn't I have noticed that before, if it was? Okay, so not divisible by 3. Getting excited about something that's not true. Okay. So we have that. Once again, the 0 is not giving us any force. So we'll have 2/3 of 9,800 multiplied by, let's see what happens here. So here we're going to get 30 squared. So we'll have 15 times 30 squared minus 30 squared divided by 3.
Shouldn't that be 30 cubed divided by 3? That's
That
cubed.
should be 30 cubed. Thank you. Yes, it should be. Thank you. 30 cubed divided by 3. And then we just have to multiply that all out. So I don't know what the easiest way to do that is. Somebody start multiplying on their calculator. If I was doing this, I would factor out the 30 squared, leaving us with 15 minus 30 divided by 3, which is 10. So whatever that gives us. And that will be in newtons. Whole bunch of newtons. All right, questions on any piece of the setup? Yeah.
What did you do to the 30 cubed divided by 3? How did it become minus 10?
So if I factor out 30 squared from there and there,
Oh,
30 squared comes out to the front. This is left with 15. There'd be 130 remaining, and then 30 divided by 3 is the 10. I'm going to type all that thing in. I can type it in during the break and get the number.
29,400,000.
29,400,000. Is that what you asked too, Caleb?
Yep.
Thank you. So, ADD area. All right, let's try. We've got one more of these. So, the hardest one. And so this last problem, called the challenge problem, this one in the book. They do a lot of these where they combine many hard things into one problem, which is kind of silly. So they're using fractions here. There's fractions all over the place here. So I've left this one in here. The answer is there. I'm hoping that if I work out one where we don't have a ton of gnarly fractions, that'll give you the sense of how to do it. And then you can try one that's more difficult if you so desire. So this is the hardest one. Anytime we're dealing with semicircles, that seems to just sort of add to the complexity. And when you deal with a semicircle with fractional numbers in it, fractional radius, that just makes it even worse. It's hard to see what the important pieces are. So the idea here is that we've got a 4-meter deep pool filled with water, and we've got this circular viewing window that's tangent to the bottom of the pool, and the radius of this viewing window is 1 meter. Okay, so we've already seen that we need to use a horizontal integration element. So we're going to go all the way across that window. So when we go all the way across that window, it doesn't matter where we draw it, but we can draw it right here. So there is our width right there. That is the width that we need to find. Now, if we're measuring horizontally, what we want to do, like we've seen in the last 2 examples, let's find the equation of the circle and then solve for x. If we solve for x, then we're measuring horizontally. This circle has a 0, 1 center, so its equation will be x squared plus y minus 1 squared equals 1. The center is 0, 1. And then if we isolate x, we would get a plus or minus, but if we choose the positive square root, that's going to give us the equation for the right half of the circle. If we chose the negative in front of that square root, we would be getting the left half of the circle. So that equation right there, and I simplified it by foiling this out, the ones will cancel. So here's our simplified form of the right edge of the circle. So this right edge right there is that function. Now it's measuring horizontally. But to get to W, what do we do with that?
Square.
Multiply by 2? Double it? Right, to get all the way across the circle, we need to double it. Okay, so that is what this 2 is right here. So right there, that is W. So W is the right half of the circle doubled. And then W multiplied by dy, all of this is the area. Ooh. All of that is the area right there. So, oh, that's a little messy now. We just want it on that part. So that is W times dy is the area that we're talking about, that strip, area of the strip. So we do what we just kind of had done in the last two problems, bring out the 9800. Is it clear that the limits should go 0 to 2? If we're trying to find the force on this window, the diameter is 2. So the top of that circle is up there at 2 y value, so we're going to go 0 to 2. And then this is our depth, 4 minus y. If this elemental strip right there, this distance right here is 4 minus y. So the value y tells you how far above the x-axis you are, and then 4 minus y would be what's on top of that. So there we have our setup. Our only hope of integrating that is with what technique at this point? U sub. It's our only chance of integrating this. So we're going to look inside, and if we were to use U sub is always the exponent, the angle, what's in the square root. Like we always pick what's inside of something and hope for the best. So if we choose u equals negative y squared plus 4y, the derivative will be negative 2y plus 4, and then we multiply the dy to both sides. Okay. That's almost what's in front. What would we do if we wanted to? We could multiply both sides of this by what so that it matches out front exactly?
4.
Oh, I guess it doesn't match that well, actually, does it? Oh, I'm sorry. I was thinking that we just had to double it and that it would match. It's not matching, though.
How did the 2y change to 4y?
Did I do... So how did this... Oh, I just typed this up the other day. That might be my issue. So where did my 2 go? Oh, I took the 2 and put it in there. Yeah, that should be a 2y.
Okay.
Yeah, I need to go retype. I just typed it the other day, and I guess I didn't look very carefully. So I took this 2 right here and multiplied it across here for a reason. Golly, sensitive. So I'm going to distribute it over here to give 8 minus 2y. That should be a 2 right there. Yeah, okay. Yeah, I thought that it was supposed to integrate pretty easily. So that's a 2. And so when we take the derivative, we get minus 2y plus 2. So it's still not going to line up exactly, is it? Okay, so we have to do a little work. But what does line up is that there's a negative 2y here and a negative 2y there. That part does line up. Okay, so here is the trick on this one. This one is tricky. Does everybody agree with where we're at right now? So the square root just comes down, pulled the 9800 out, took this 2, distributed it here to give a 8 minus 2y. The only reason I did that is that I see that the derivative here is going to have a negative 2y in it. You could create a fraction if you didn't want to distribute that 2. You could have pulled the 2 all the way out and you'd end up with a fraction. Doesn't matter. So here is the clever trick here. So we've got the 9800 and the integral. Here's what we're going to do. We see that this derivative is negative 2y plus 2. What I'm going to do is rewrite this part right there as 6 plus 2 minus 2y. And you're like, okay, wait, why would we do that? Well, the reason that we are going to do that is that now that part right there, that is going to be the derivative piece. And what we're going to do, here's the clever part, all we did was separate the 8. We can distribute this square root to two different terms here. We can distribute it here and we can distribute it here. One of those terms is going to have a perfect U substitution because the derivative of what's inside is going to match. So we will have the following. So we're just distributing. So we're going to have two integrals. First, I'm going to take the square root and multiply it by this 6. So that'll be one integral. Then we're going to add to it the integral where the square root is distributed to the 2 minus 2y.
May I ask?
Of course.
So the line above what you're doing right now, the line above that, like, that's just the next step after. So how did you get the 6 again?
So
math.
this, I turned the 8 into 6 plus 2.
Oh, so okay.
Right? 6 plus 2 is 8. If we rewrite that 8 as a 6 plus 2, then we are creating this negative 2y plus 2 piece.
Okay.
So we're just sort of looking and saying, okay, well, it doesn't match exactly, but if we take that 8 and break it into two numbers, if we break it into a 6 and a 2, and we sort of group the 2 with the negative 2y, then it's going to match that. And we know that we can distribute, right? If you turn this into two terms, we can distribute the square root into both of those terms, and the integral symbol can distribute across a sum. So if we distribute the square root to the 6, that's going to be one integral, and if we distribute the square root to this 2 minus 2y, that'll be our second integral. So it's just obvious.
So you're just manipulating the equation.
Manipulating it, this is harder than what we would put on a test, for sure. But like on a quiz or a homework question, you should be able to fumble through this with a couple of examples. So, there we have our thing. Let's focus on this. Let's do one integral at a time just to not sort of make it to try to minimize the complexity. Let's just focus on this right integral. So we're going to let u be that, and du is the outside. So we're going to leave this other stuff alone for a moment. Let's just forget about this other stuff for a moment. I'll factor the 6 out to the front. We'll pretend that that's like a big dramatic step. We're only going to we'll just do that one piece. Over here, this is the one that's going to become super interesting. So we get square root of u, right? And then 2 minus 2y times dy is du. So there's the second integral. Now let's look at the limits of integration. When y is equal to 0, what is u equal to?
0.
0. When y is equal to 2, what is u equal to?
0.
0. And what is the integral from 0 to 0?
0.
0.
It just cancels out.
That's just gone. Integral of 0 to 0, adios. Not here. Its value is 0. All right, so now we're like, okay, we're getting somewhere. Let's factor this 6 out to the front. And so here's what we are left with. This is a non-integrable integrand at this moment, but we know what the geometric interpretation of that integral is. We know that that function is right here, right? That is the right half of the circle of radius 1. right? That's the right half.
It should be 2y, shouldn't it?
Yes, it should. In here, there is a 2. Thank you. Good catch. So that function right here, this function, is right here. That is the right half of the circle. So this represents how much of the area of the circle?
Half of it.
So if we were to integrate from 0 all the way up to 2, we are going to get the area of that semicircle to the right. And that's what we're doing. So this is going to be area of semicircle. So that right there is the area of the semicircle. So we're going to end up with 9,800 multiplied by 6 multiplied by area of a circle divided by 2. The area of a circle is pi r squared. The r here is 1. So it's pi times 1 squared divided by 2. So we're going to end up with 9,800 multiplied by 3 multiplied by pi, and we are finding newtons. So this will be 0, 0, 24. That, if I multiply right, that will be our answer. It doesn't seem.
100, 400,
29.
Yeah, it feels like that's not right.
1,000.
0, 0, 24, 20, 29. Yeah, thank you. 29. Right, because we're subtracting 200 3 times, so we're subtracting 600 from 30,000. Okay. And that thing is a 0, no matter how terrible it looks. So that is our cumulative force on that little window. So that one is that is the hardest one in this chapter. And that integration technique to even, sort of think about breaking that 8 into a 6 and a 2, that is definitely complicated. I wouldn't put one this hard on the test. All right, is there any part of that you want to ask about that?
So how much of the information given here would we actually get on a test?
You would be given, you're not going to be given the formula here,
Yeah.
but you're going to be given that gravity is 9.8 and density is 1,000. You would need to know how to find the equation of a circle and to solve for the x. So that stuff you would have to be able to do.
Okay.
These other two are much more reasonable test questions. Because, that one takes this takes long enough. And that's the simplest type of one.
Will we be given like the figures or like the drawings or no?
So it depends on what, if you're told that the tank is cylindrical or something, probably not. If it's a cone, though, I would probably draw it for you. So if you look back at, one good thing to look back at when you're preparing for the test is to look at these prior exams. So I put the last 2 exams that we've had in this class. So here we had a parabolic trough, so I drew it, and here we had a actually we just did that one, right? Trapezoidal face on a dam. So there'll be images if it seems a little complicated, but maybe not if it's a cylinder. So both of these with the answer keys are there. So let's see what we had down here. So here we had a rectangular window in a pool, so that's actually a lot easier than the ones we just did. And then part of a cone, frustum of a cone. Yeah, so you'll have some images, for sure. All right, so in terms of what is happening, you have homework and quizzes. Those are going to be due next Wednesday night at midnight. Homework and quizzes in my math lab. Worksheet is due tonight by midnight, but I'm not going to open it until tomorrow morning, so if you work past midnight, totally fine. I will grade those tomorrow morning so that you can then have a full week to figure out the mistakes and get your corrections done. Tuesday, I could not get a sub for, unfortunately. So the review, again, there's a video for every single review problem, and if you hit the play button here, it plays in that tiny little window, and you can kind of, if you are good with your mouse, you can grab the bottom corner and make it bigger if you want. If you just click on the title, though, it'll open up full screen in YouTube, or you know what I mean? It'll open it up in YouTube, and you can make it as big as you want it. But if you just hit play there, it's a little finicky with the, there's the corner of the box that it's sitting in, and then there's the corner of the video, and if you have to get to the corner of the video if you're going to try to stretch it. Tends to be just easier to click on the title, and then you have full real estate. So every one of those is available to you. I will be out of cell coverage Sunday and Monday. I'll have cell coverage again on Tuesday. So if you have questions, I can get back to you Tuesday night, all day Wednesday. But those 2 days, Sunday and Monday, I'll be out of touch. So our last topic is hyperbolic functions. And they sound harder than they are. And you aren't going to see them a ton when you go on, unless maybe you go into architecture. They'll use hyperbolic functions for certain things in architecture. The hyperbolic functions, they have very limited applications, but if you're dealing with one of those applications, they're really helpful. It reminds me of a topic which you may or may not have heard of called quaternions. Has anyone heard of quaternions? So you all know that if you're dealing with imaginary numbers, I times I is -1. And if you extend the complex numbers, you get this set of numbers called the quaternions. And they're super interesting. They have a lot of cool properties, but there's only one application, which is why most people never even encounter them. The one application is rotating a solid object in three-dimensional space. So the one application is with satellites. It's the only use of quaternions. And it's like they don't even weave them into most courses because it's really just that one application. So anyone that ends up dealing with satellites, it creates a very easy, quaternions create a very easy way to rotate a solid object in three-dimensional space. And so if you are going on to that type of engineering where you're going to end up doing aerospace or something, you will encounter quaternions for sure. And it kind of reminds me of the hyperbolics. It's like, okay, when you find the application for which it's useful, it's really useful. But a lot of times you are not going to go into any depth because you encounter those applications in just very narrow areas of engineering usually. So, and that's what hyperbolics are. There are uses of the hyperbolics, but they're going to be limited. So for our purposes here, we're just going to introduce hyperbolics. We're going to learn how to take some derivatives and learn how to take some integrals, but we're not going to get that tangled up in them. So it's going to be fairly straightforward. And the nice thing about the hyperbolics is that they parallel the regular trig functions beautifully. And when you think about the regular trig functions, most books will call them the circular functions. Not all books, but many books will call them the circular functions because they're defined from a unit circle, right? You're looking at the ratio of the radius and the x-coordinate and the y-coordinate. Right? You do x over r, y over x. You form your 6 ratios. So they're called the circular functions because they're based on a circle. The hyperbolic functions are based on a hyperbola. And so the circular functions are based on this unit circle. We look at the right half of the unit hyperbola. If we were to graph the entire hyperbola, there would also be a left branch. But as far as the hyperbolics are concerned, we just look over here to the right half of the coordinate plane. We're only looking at the right branch of that unit hyperbola. And there's this interesting connection between the two. you do not need to know this. This is just sort of a little bit of development. If you look at the unit circle, what you should have taken away from trig is that if you're on the unit circle, the angle and the arc are the same. The angle and the arc are the same. And the reason that is true is because we have this formula, and it depends on how you remember it. Let me just write down the three pieces to this formula first, and you tell me how you remember it. So there is a relationship between theta, r, and s. And what is that relationship?
S equals R theta.
S equals r theta. And if you can either remember it like that, S is equal to r theta. The way I was taught to remember it is that theta, now this is only when theta's in radians. S and r have the same units of length. They could be inches or feet or miles or meters or whatever. And the way I was originally taught it was that theta, this rotational angle in radians, is like a rotational slope. It's S over r. And if you multiply both sides by r, a lot of times books will sort of present it in this way. Either way, doesn't matter. Those are both correct. What are the units on theta?
Radians.
We call them radians, but radian is not really a unit.
It's a unitless measurement.
It's a unitless concept. Why? Because S and R have the same units, and those units cancel. So when we say radians, all we really mean is not degrees. That's what a radian is. It's not degrees. Degrees are like an arbitrary, oh, we're going to break the circle into 360. Radians are just, they're a pure number. S divided by R has no units. So it's a unitless number, but we write radian just to emphasize that it's not degrees. But you really don't even need, if you know you're measuring an angle, you don't have to put RAD. It's understood. If it's degrees, you have to put the degree symbol. But if you don't put a unit on it, it's understood to be radians. And you'll see that in pre-calculus, you probably saw it, where there's a formula that says the linear velocity is equal to the angular velocity times the radius. Well, angular velocity is always sort of given in radians per unit of time, so perhaps radians per second. And then if you multiply by the radius, that's meters. But the units for linear velocity are meters per second. So they just sort of use the radian there because it sounds weird to say angular velocity is, whatever the number is per second. To say 5 per second is just weird. So you say 5 radians per second to emphasize that it's angular velocity. But then when you multiply by meters, you never would put the radian in down here, even though technically, if you're putting it there, kind of feels like it should be there also. And so that's one of those examples in pre-calculus where you see that, oh yeah, radian can be there or not be there. It's kind of whatever is convenient. But it is a unitless number. So if we are dealing with the unit circle, so if r is 1, then s and theta are the same. Right? So the arc out here and that angle, they're the same. The magnitude. So yes, the arc would have units of length, and the angle we would say it's got units of radians. But the arc and the angle are the same. They're both t. That tells us that the area of the circle, we know that the area of a sector is 1/2 theta times r squared. So if r is 1, the angle divided by 2 is the area of the sector. If we use a t for that angle, the area of the sector is t divided by 2. You could solve for t and say that the t value is 2 multiplied by the area of the sector. Again, just sort of an interesting tidbit. Area of a sector multiplied by 2 will always give you the angle. That's the connection with the hyperbolic here. This hyperbolic, we don't really call it an angle, but a lot of times we'll call it a hyperbolic angle, just to sort of parallel calling that an angle, even though there's no angle t here. right? There's no rotation. Like when we say the angle is t here, you're imagining rotating by t radians. Here, that t does not mean any sort of rotational thing, but we will refer to it as a hyperbolic angle, even though it doesn't have the same concept of angle. And this area right here will in fact be twice the area, or the t value will be twice the area of that hyperbolic sector. So that's the connection between the two in terms of their development. And that connection will lead us to these following definitions. So for the hyperbolics, unlike the circular functions, unlike the trig functions, there is a very simple definition involving exponentials. You will see later this semester that the circular functions can actually be defined with exponentials also if you allow for the imaginary unit, I. Anyone know what the most famous formula in all of math is?
E to the I pi equals -1.
E to the... So a lot of times what they'll do is write it this way. So e to the pi I plus 1 is 0. All 5 of the most important constants in math in one equation. What did Euler do when he discovered that? Can you imagine discovering all the 5 constants that we use most in math to this one simple formula? Like there's nothing extra in it. It's crazy. So that formula, we will see why that formula is true when we get to infinite series. And that formula is going to sort of be illustrated with how the circular functions, sine and cosine, are connected with the exponential function. A little more complicated. With the hyperbolics, it's actually pretty straightforward. So the hyperbolic cosine, the way you can think of this is that it's the average of exponential growth, e to the x, and exponential decay, e to the negative x. The hyperbolic cosine is the average of exponential growth and decay. Hyperbolic sine is the average difference of exponential growth and exponential decay. So those are the 2 definitions for, I will pronounce them sinh and cosh. Sinh and cosh. There are others, some people will call this cosh. The hyperbolics are used so infrequently that there is not uniform language throughout the planet. People will call them different things. So I will refer to that as sinh. I'll refer to that as cosh. So those are their definitions. And they will lead to the definitions of the other 4 hyperbolics. So tangent, hyperbolic tangent, we have this parallel with the circular functions will be sinh over cosh, just like tangent is sine over cosine. So we're going to really emphasize this parallel connection. Similarly, hyperbolic cotangent, which most people will call cotangent, tangent and cotangent. You could call this sinh and cosinh, but most of us will just call that cosh. But tangent and cotangent will be reciprocals of each other. So instead of sinh over cosh, it's cosh over sinh. So you can create this definition for each of the 6 hyperbolics as exponentials, some sum or difference of exponential functions. Now again, we are going to be looking at, we're more interested at this stage in derivatives and integrals. So you don't have to memorize these at this point. You'll have some homework where they ask you to simplify some things. But for us, on the test, we're focusing on derivatives and integrals. So still, we're just getting through this development phase, looking at the parallel connection between hyperbolics and circulars. Now we come down here. With the circulars, we've got the primary Pythagorean identity, sine squared plus cosine squared is 1. Like that leads to all the identities. For the hyperbolics, you have a comparable identity, but it's a little different. Cosh squared minus sinh squared is 1. So that is the fundamental identity for hyperbolics. Let's jump to the next slide for a moment and try to get a visual for what the heck is going on. So the hyperbolic cosine, we said it was the average of growth and decay, exponential growth and decay. If you look at these two dotted red lines, that one is exponential decay, the other one is exponential growth, and when you add the exponential growth and decay, you get this shape here. It's not a parabola, it's the hyperbolic cosine. It is the shape of the hanging cable. So back in the day, one of the Bernoulli brothers posed that question, what's the equation of this hanging cable? You got two towers and you've got a cable hanging between them. What's the equation? You cannot graph it with a parabola. You cannot create it with any polynomial. It looks, like it looks like it should be a parabola, but it is not. You can prove that it's not a parabola. It is e to the x plus e to the negative x divided by 2. It is the hyperbolic cosine. So that is the hanging cable, which is a place where if you're an architect, a lot of times you'll take the hyperbolic cosine and flip it over to create the strongest possible arch. St. Louis, right? The strongest possible arch that can hold its own weight is the upside down hyperbolic cosine. So the hyperbolic cosine looks parabolic, but it's not. The hyperbolic sine, sinh, is going to look a lot like x cubed. But it's not x cubed, but it looks kind of like x cubed. And they will approach each other asymptotically, never crossing. So hyperbolic sine looks like x cubed. Hyperbolic cosine looks like y equals x squared plus 1, but it's not. Knowing these graphs tells us two pieces of information. If we know that the primary identity is cosh squared minus sinh squared, this reinforces that. Right? Cosh squared, cosh is above sinh, so if you square it, you'll get a positive number. If you were to do sinh squared minus cosh squared, you would end up with a negative number. So this picture at least helps us remember the order, that cosh comes first in that equation. Cosh squared minus sinh squared is 1. We also see that cosh is always positive. So if we ever come up with an absolute value of cosh, we don't really need the absolute value bars because cosh is the hanging cable, it's above the x-axis, it's never negative. So the graphs are helpful in that you can do a couple of things with those graphs. All right, so let's stop here and we'll talk about some of these identities, which ones are important, which ones aren't, when we get back from our break. Let's do our 10-minute break. Now, break! So looking at these identities for the hyperbolics, again, we're not going to get into the weeds with these identities. We're focusing on derivatives and integrals. So we're just sort of looking at the parallels between the hyperbolics and the circulars right now. And this fundamental identity, it's not really a Pythagorean identity because we're not dealing with triangles, but it's like the Pythagorean identity. So this identity, this primary identity for hyperbolics, is going to lead to these other two identities, just like in the circular functions. That primary Pythagorean identity led to the other two ones. You divide it by cosine squared or sine squared, and you got the other two. So there is that parallel here. There's also the odd-even parallel. So when we're talking about cosine, we know that the cosine function is symmetric about the y-axis, which makes it an even function. So even functions like the parabola are always symmetric around the y-axis. If you go over x or go over negative x, you come up to the same height. Right? That's what it means to be parallel about the y-axis. That's what it means to be even. So an even function, if you go to the right x or to the left negative x, your y coordinates match. Your values will be symmetric about the y-axis. So same thing here. Cosine is even, and cosh will be even. We can see that by the graph of the hanging cable. Sinh is going to be odd, just like sine is odd. So with sine or sinh or an odd function, if you go x and you go negative x, you're going to have opposite y coordinate values. So the y value on one side will be up, the y value on the other side will be down that comparable amount. Tangent and tanh are both odd also. So lots of parallels. This identity, you'll see this, one of the, so these are also called power reduction identities. Those will show up if you ever have to integrate cos squared or sinh squared. I wouldn't put it on a test, but on a homework question, if it says use an identity, that's what we would need. To integrate sinh squared or cos squared, we have to reduce the power. And then there's the parallels with the sum and difference identities and the double angle identities, but again, those are not things you need to memorize at all. More interested in derivatives. Okay, so let's go ahead and do some derivatives. So we've talked about the graphs again. Looking at it, you see that sinh is an odd function because it's symmetric about the origin. If you go right and left the same distance, you go up on one and down on the other. That's what it means to be odd. That's what it means to be symmetric about the origin. And for cosh, you see that, okay, it's symmetric about the y-axis, which is what it means to be even. I guess I didn't need to do that. So let's get to our derivatives and integrals. They are very similar to the circular derivatives, but there's one major difference. When we look at our primary three, so sinh, cosh, and tanh, those are our primary three, just like sine, cosine, and tangent are the primary three circulars. Notice that their derivatives are all positive. So we have the parallel thing going that if you differentiate cosine, you get to negative sine. They are essentially each other's derivatives. Here it's the same thing, except you don't have to deal with the negative. So derivative of cosh is sinh, derivative of sinh is cosh. They are exactly each other's derivative. You don't have to multiply by a -1 for one of them. So derivative of sinh and cosh are each other. Derivative of tanh, very similar to derivative of tangent. Derivative of tangent is secant squared. Derivative of tanh is sec squared. So the main thing is that the right-hand sides are going to be very similar to the circular functions. You just have to get the signs right, the pluses and the minuses. And if you remember that the primary three, sinh, cosh, and tanh, are all positive, that means the other three are all negative. So if we go to the other three down here, we are going to see that all three are negative. And you have the parallel piece to it. The derivative of cotangent is negative cosecant squared. This will be negative cosec squared. The derivative of sec will be minus sec tanh. So there's the one that's different, right? These two are the two that are going to be different from circulars. That one and that one. So because the derivative of cosine is negative sine, the derivative of secant is sectan. But here we just have to remember that top three are positive, bottom three are negative. But the functions in there line up with the circular functions. Anytime you have a derivative formula, of course you have an integral formula. You just go back the other way. Down here, we are not going to deal with the integral of sec or the integral of cosec. Not going to deal with those. We will deal with these other two, though. The integral of tanh and the integral of cotang. And it's not hard. If you do the following. So if we wanted to integrate tanh, tanh is sinh over cosh. And we talked last week, and even on Tuesday, about an integrand that is in logarithmic form. So recall that an integral is in log form. If you look at the integral of 1 over x dx, what does that integrate to? What's our antiderivative?
Absolute natural log.
Natural log absolute value. Uh-huh.
Yeah.
Like that. This is in log form because the denominator's derivative is the numerator. Anytime we have something in log form, so let's just say we have x squared plus 1 right here, and down below we have, let's see, so x cubed, so that's going to be 3x. So let's do this. Almost there. I'm thinking on the fly here. So let's suppose we have that. Isn't that denominator's derivative the numerator? If that's true, then we're done. This is going to be natural log of the absolute value of the denominator. So anytime, question?
For number 1, isn't the cosh supposed to be in absolute values?
Right here?
Yeah, yes or no?
No,
No.
because cosh is always positive.
Oh. Oh. Okay.
Could you put it? Yes. Because you do natural log of the denominator,
Yeah.
but because that function is never negative, you don't need the absolute
You
value.
don't need to. Okay.
Right, make sense?
Yeah, that makes sense.
So on this one, sinh is an odd function that goes down into quadrant 3, so it can be negative, so we have to put it there.
Okay.
Yeah. So this is what we mean by log form. If the denominator's derivative is the numerator, the answer is always natural log of the absolute value of the denominator. If that denominator is never negative, you don't have to have the absolute value bars. So when we look up here, that's in log form. Now, if we didn't recognize it as log form, what would we do? We would let u be the denominator. So you can always get away with doing it the longer way if you don't recognize that it's in log form. But this is how it's going to simplify. You're going to end up with, okay, if we let cosh be u, then sinh times dx is du, and then we get natural log absolute value of the denominator. And then this is going to be natural log of absolute value of cosh. And then we say, oh, well, cosh is never negative, so you can take away that absolute value bar, that absolute value symbol. But if you recognize that something's in log form, you can just cut to the chase. And the easy way for me to know that you know that it's in log form and that that's what you're doing, you can just do something like that. Put a little LF, so I know that you're seeing it as log form or that you think it's in log form. That's how you're getting your next step. So all of these guys, like if you have some random one here, you can just put an LF there. It's log form, natural log of the denominator. So that's how you're going to get at those, the tanh and the cotanh. They are both in log form. So let's go to some others. Just like in Calc 1, we are going to develop the other derivatives from the two primary derivatives. So in Calc 1, you went through that whole limit process to figure out that the derivative of sine was cosine and the derivative of cosine was negative sine. Maybe you blocked that out of your mind, but you did a whole limit thing, and you ended up proving those two. Once you have those two, you can figure out everything else by using your rules. Quotient rule, product rule, chain rule, power rule, all those things. So I'll do the first one, I'll let you all try the second one. So here, if we rewrite this in terms of cosh or sinh, then we can use these two basic facts and we can generate all the derivatives that we want for each of these functions. So which rule are we going to use here? Derivative of A? Product or quotient?
Quotient.
Quotient. So quotient rule starts with low D high. So low is the function in the bottom, the lower function. High is the function on top, the higher function. So we go low D high minus high D low over low squared. So low, what's the derivative of the numerator?
0.
0. So we're starting with low. We don't need to write this all out because we're multiplying by 0, but I'll write it out for this first one. So low D high minus high D low, the derivative of cautious inch. All divided by low squared. So high D low over low, high D low, low D high minus high D low over low squared. So we end up with minus sinh of x divided by cosh squared. And here's where it's helpful to write this cosh squared in a product form here. And in the numerator, it's helpful to think of that as sinh times 1. And then you can just break it apart and see that, okay, 1 over cosh, that's sech. Sinh over cosh, that's tanh. And usually we write it in not tanh sech, usually we write it as sech tanh. Not that it matters. Commutative law of multiplication is true. So we'll get that. Any part of that you're not sure about? Or you all do 21 then, same idea. Rewrite cosec in terms of sinh or cosh, use the quotient rule, and just make sure that you can run through it. And I'll do a quick roll while you're doing that. Mohammed, Bell, Kim, Andres, here, Marcus, Ethan, Sean, Maximus, Annie, not here, Alexander, Shay, Caitlin, not here, Stockton, Nathan, Mason, Maxwell, Caleb here, Garrett, Saxon, did I see him earlier? Katura here, Eric here, Jesse, Will, Tyson, Milan, not here. Any trouble with the cosecant one? Straight application of that quotient rule. So if we wrote it out, we would say d dx 1 over sinh. And then the quotient rule says low d high, which is 0. Derivative of 1 is 0. Low d high minus high. High is 1. Multiplied by d low. So have that. Over the denominator squared. Again, we can sort of imagine splitting the denominator into a sinh times a sinh and introducing a 1 in the numerator just to sort of make it cleaner. 1 over sinh is cosec. And that's cotang and a minus. So cosec times cotang. So that's how we get to, bless you,
Thank you.
all those other derivatives.
Are we going to go over it out to actually find what each of those values, like if we were to plug in something for x, what the value would be? Okay.
No. No. Yeah, we're just going to look. So the circular functions, we have the unit circle. So we have all of those angles that we can find trig values for really easily. We don't have the same convenience with the hyperbolics. The only thing we know is that sinh of 0 is 0, cosh of 0 is 1. Those are the main two values that we know.
Okay.
So yeah, we aren't going to have that. That piece will not be parallel. It's way more complicated than, unfortunately. So let's try some derivatives. So remember in our mind, we're thinking about the parallel connection with the circular derivatives, but we have to remember that sinh, cosh, and tanh are positive, the other three are negative. That's sort of the one thing that's really easy to screw up. So we just have to remember that. Okay. So derivative here for the first one, f prime of x. I'm thinking of this, if it's helpful to you, if you're less likely to make some sort of arithmetic error, write that square root as a half power. So then we use the power rule. Power rule says bring down the exponent, leave the base alone, subtract 1. So we're going to have the 1/2 multiplied by, okay, we're going to leave the base alone, okay, and subtract 1. So we're going to have cotang to the negative 1/2. So that's the power rule part. Now we have to differentiate the base. So this part in here, this is the bit, where'd the 3 go? So this part down here is the base. So now we have to differentiate the base. So we look at the outer function cotang. That's one of the second 3, so we know that its derivative is negative. So we're going to have a negative in there, so multiplied by negative. So if we start thinking about the circular functions, the derivative of cotangent is negative cosecant squared. So the only difference is this will be negative cosec squared. So negative cosec squared of the same angle. Now we have to go into the angle and differentiate that and get a 3. So our last piece, and this now we're doing chain rule stuff. So there is our derivative. If we simplify this, we would have negative 3 cosec squared of 3x divided by 2 times the square root of cotang 3x. And that, unless the question says go back to cinches and coshes, you can just leave it like that. If they wanted us to go back to cinches and coshes, there would be some other combining of things that we could do. But let's just leave it as is. Okay, you all try this one. So find the derivative of natural log of sec of 2x. So if you want to put parentheses in there to sort of help identify the outer function and the inner function and the innermost function, you can. Let me know if you're stuck on one of the steps and I can come and nudge you. Yes. Yeah, so on the board I wrote those big parentheses, so if you want, you could put those, because sometimes not having them makes it, you know, you can sort of think it isn't what it really is. Yeah, that's the first step. Mhm. This one will have some cancellation that you can definitely do. There we go. And so, should this one have a positive or a negative derivative? Think about such. Right, because it's one of the second three. The primary three are sinh, cosh, and tanh, and so such is part of that second three, so it'll have a negative derivative. Yeah. And then how about your angles here? Should those be just x's or? Yeah. There's a lot of,
Just one A, just
right?
one A.
There's almost
You do 1 over
All right, so when we do this derivative here, the outermost function is the natural log, and the derivative of that is 1 over whatever's on the inside. So that's the outermost derivative. And then we have to multiply by the derivative of the inside. Such, super easy to want to make it a positive derivative, but it's part of the second three. Sinh, cosh, and tanh are the primary three, and the secondary three have all negative derivatives. So it's going to be negative, but then it's going to parallel circular functions. Derivative of secant is secant times tangent, so that'll match. So we're going to get sech of the same angle multiplied by tanh of the same angle, and then multiplied by 2, the derivative of the angle. Here we definitely have some cancellation. We can take that sech of 2x and that sech of 2x and wipe them out. And so we'll be left with negative 2 multiplied by tanh of 2x. So the hyperbolics in general, practice them enough, because this is really a pretty easy part of the test, is the questions with the derivatives and integrals here. They're not hard, but you just need to do enough practice. It takes a little less practice to get these down than some of those volume problems. All right, let's try another one. So here, we're going to do product rule. So the primary operation that we see is multiplication for these. I'll do the second one since that one looks nastier. Bless you.
Thank you.
So if we're doing product rule, remember we think about a first function and a second function. So I'm going to sort of highlight what I'm thinking of. I'm going to think of that as the first function, the x squared, and I'm going to think of the cosh squared as the second function. One thing that you have to remember that can be a little bit confusing is that when we write y equals sine squared of x, remember that that's really sine of x quantity squared. Trig functions are the one function where we sort of use that, although this book actually does it with natural logs too, which is the first time I've ever seen that. But usually it's only trig functions where you use this funny shortcut for a power. And it's very tempting to mess up your derivative. So remember that the derivative here, if you write it with this power on the far outside, it's a little more obvious that that's the outer function, is the squaring function. And so you should have 2 sine to the 1 power. That's the power rule part. Bring down the power, subtract 1. And then you multiply by the base. So you multiply by cosine x. So that's how we would differentiate the square. So we have to just be careful with that square there. We need to do something similar. If you need to rewrite it as a square on the outside, of course, do it. So here we're going to go first function. So first, derivative second. And the derivative of the second first, the power rule part will be 2 cosh of 3x. So power down, subtract 1. Now we have to differentiate the base. The base is cosh of 3x, so its derivative will be sinh of 3x. And then we differentiate the hyperbolic angle, which gives us a 3. So that's first, derivative second. And you've seen the product rule in different ways. When I do it, I will always do it this way. First derivative second plus derivative of first times second. And I argue that that's the best way to do it. I mean, a lot of people will say first derivative second plus second derivative first. You know, there's all sorts of ways. But when you get into calculus 3 and you are differentiating vectors that are being multiplied together, you have to do it in the first derivative second plus derivative first times second way, or it'll be wrong. So when you have two vectors that are being crossed, so if you have v cross w, if you've had physics, you know v cross w, what it means. But v cross w is a product of vector functions, and the derivative only works if you do it in that order. So getting in the habit of doing it that order is just helpful. First derivative second plus derivative first second. Okay, so that's what we have here. Now we have to do the second part, the derivative of the first multiplied by the second. The derivative of the first is simply 2x multiplied by the second. So that's where we're at. And there's not a lot of simplification here. The 2 and the 3, so the only thing I'm seeing is that we can make that 6x squared. Cosh times sinh. A lot of times they like to write sinh first. Of course, it does not matter because the commutative law of multiplication is a thing. And I guess there's nothing we can do over there either. So yeah, not a lot of simplification.
Shouldn't that cosh at the end be 3x?
Yes, it should. Thank you. Yeah, it's so easy to. Good catch. Yeah, cosh of 3x. Thank you. Okay, you all try the first one up there. That one's not quite as messy. Make sure you can execute your product rule. Even if you're kind of a snag, if you go fast.
That was a little easier.
Put your head. Let me ask you one question. Derivative of tangent. Yeah, yeah. That's the identity for tangent, but not its derivative. That's secant. Yeah, derivative of tangent is secant squared. Derivative of tangent will be.
I was doing it too fast.
Yeah, that looks. So, first thing, we're going to do first derivative second. So tangent is one of the primary three, so we know its derivative is positive. Derivative of tangent is secant squared, so derivative of tangent will be sec squared. and it's going to be positive. So first derivative, second, plus derivative of first is just 1, and 1 times tangent is tangent. So there we go. No simplification there. All good. Okay, so up here, we have a product, and we're trying to integrate a product. At this stage of the game, the only way product integration has really worked is if substitution could be used. And when I am looking at this, I am seeing the product of tangent, I should say, and sec squared. So there's really 3 choices for u, but the most obvious choices were to let u be tangent and to see if its derivative is present, or to let u be sec squared and see if its derivative is present. Is there one of those that has the derivative more obviously present?
U should be tangent.
Tangent is a great choice. It's not the only choice, but it is the easiest choice. Because if we say, let's let u be tangent, well, tangent, again, it's one of the primary 3, so its derivative is positive. Derivative of tangent is secant squared. So this derivative is, in fact, sec squared. And so we're flying right off the bat. This is just going to be u du. And the integral of u is u squared over 2 plus c. Now we back substitute, so we're going to end up with 1/2 times tangent squared of x plus c. So at this stage of the game, if we see a product, we really want to be leaning into substitution right away. Same is true for a quotient. Most of the time, our quotients we've been using substitution for. So when you look at that second one, what are you thinking? If you were going to let u be something, what would you let u be?
1 plus cosh.
Yep. We want it to be the denominator. Usually we want it to be the inside of something. The angle, inside the exponent, inside the square root. If we're dealing with a fraction, most of the time we want to let u be the denominator, because then its derivative hopefully is the numerator, or some multiple of the numerator. This one has an extra special quality, though. The denominator's derivative is what? Which is the numerator. So we're done. It's immediate. It's in log form, so we could have just jumped right to natural log of absolute value of the denominator. And then, if we're observant, we realize that the argument of this natural log is never negative. So we don't need those absolute value bars. So we could cut to the chase pretty fast. How about if we had something like this? What about if we had, I'm going to modify this just a little bit. What about if we had that? What is the derivative of the denominator? 4 sinh. Derivative of cosh is sinh. We've got a multiplier of 4. So it's not quite the numerator. But is there a way that we could rewrite this so that the derivative of the denominator is the numerator?
Can't you just pull out the 4?
No, we have to be careful. There's two. Let me show 2 ways. Do you agree that we can multiply by 1? Yeah, you agree we can multiply by 1. If we multiply by 1 in that form, now it's in log form. Now it's in log form, and we could say, okay, that's log form. So we have a 1/4 out in front, and then it's going to be natural log And let's just recognize the denominator is never negative, so we don't have to do the absolute value business. So that is one way. And I also heard, oh, pull out the 4. That's also an option, as long as you know how to factor. So if you pull out the 4, it's in the denominator. What is the denominator going to be once you pull out the 4?
Cosh x plus 1/4.
Yes. Cosh x plus 1/4. Super easy to make a mistake there and just sort of leave it as plus 1. Remember, if you're factoring out that 4, it's got to come out of both terms. Now, this is in log form again. Right, that's log form. The derivative of the bottom's the top. So here we would get 1/4 natural log of cosh x plus 1/4 plus c. So both of those are the same. Both of those work. They look different, but they are the same. If you were to graph both of those, they would have the same exact graph. Okay, any questions on those? So log form, it helps. If you can recognize log form, it just will save you some time for sure. All right. Why don't you all try number 40, try this first one. So we're seeing a product. Right? There's that function and there's that function. So the two natural choices to think about first are, should we let u be cotangent squared? Should we let u be cosec squared? That's sort of the first choice. Then you start realizing, oh crap. If you were to let u be one of these things squared, isn't the derivative really nasty because you'd have to bring down the 2, subtract 1, and then multiply by the base? So those aren't real options to let u be the whole thing squared. So think about maybe not let u be the whole thing squared, but maybe just one of the bases. You know, maybe u as cotangent or u as cosec. So think about those. Find the one that seems like the plausible substitution. So ideally, if you, whatever you choose for u, its derivative is obviously present. That's ideal. And remember, if you do u substitution, you have to turn all the x's into u's. So everything has to be turned into u's. So you will find that one substitution works way better than another candidate. So what do we think? Should u be cotangent or cosec? So if we go with cotangent, let's see how that plays out. So the nice thing about choosing cotangent, first off, remember that it's part of the second 3, so its derivative is negative. And what will its derivative be?
Negative cosec.
So negative cosec squared. And that matches exactly this whole second factor. So this is going to be the best choice. So we will end up with cotangent squared, so that's going to be u squared. And then cosec squared multiplied by dx is right there. So that's going to turn into a negative du. So the negative can go out in front, and then the du. So that would be the simplification. So then we're going to end up with negative 1/3 times u cubed plus c. And then we back substitute and get our cotangent replaced with the u. So cotangent cubed of x plus c.
So why don't you set u to cotangent squared and just cotangent instead?
Did you say cotangent squared?
I already see the reasoning for that.
So if we do cotangent squared, we're going to bring down the 2, subtract 1, so we end up with
A far larger.
a far larger
Yeah, du.
du that's not going to match, not going to match enough. And now what about the other candidate was, oh, what about this one? That's also a candidate, but let's see what happens here. Derivative of cosec is going to be negative, that's going to be negative cosec cotangent. So let's see, so if we let u be cosec, we've got to be careful here. So u is cosec, so I'm going to put one u out there. I'm going to take one of these coseches and give it a u. But we need a cosec cotangent for du, so we're going to have that. But what is also still there? Another cotangent. There's still another cotangent of x. So we would have to deal with that. That would have to be converted to u somehow. And so we'd have to come in here, do some manipulation, and we could possibly do it, but it's going to be way more complicated. So the substitution that makes the most sense is going to be let u be cotangent, because its derivative is present. And you don't have to do any other manipulation. All right, let's try this one. So here's one of these ones where, like on that one homework problem where you had an integral of cosine squared or sine squared, you have to power reduce. Same is true in hyperbolic land. We need to somehow power reduce this. And let's just go back to the identities for a minute. If this was going to be on the test, I would give you the identity. So these two right here are called the power reduction identities. And they're basically half-angle identities rewritten. And when we say power reduction, notice that the power on the left side is 2, the power on the right side is 1 on the hyperbolic function. So that's the key for integration. If we have a power of 2 with sinh or cosh or sine or cosine, you have to use an identity to get the power down to 1. So that is going to be our identity, cosh 2x minus 1 divided by 2. So there is our integral. The 2 in the denominator, the thing that makes the most sense is to factor that out to the front so that we can then integrate term by term the numerator. All right, so let's see here. We've got to be a little bit careful. Integrating cosh 2x. So outer function is cosh, inner function is 2x. the integral of cosh is sinh. So the nice thing about the hyperbolics is that they are exactly each other's derivative and integral. But now that angle is not just x, that angle is 2x. It's a linear function of x. So what are we going to do with that? Divide by 2. The derivative of that angle is 2. Because we're integrating, we divide and not multiply like we would if we were differentiating. And then the integral of -1 gives negative x, and then we have a plus c. The best way to write this final answer would in fact be to distribute. It's not wrong not to distribute, but we would usually distribute here for this reason. If you are going to factor, the whole point of factoring is to find zeros. And if you're going to find zeros, you have to have the entire thing factored, not just 2 terms. Like that is not leading us to any zeros over there. So for example, if you have x squared plus x plus 1, you would never do this. Right? You wouldn't write it that way. Right? That doesn't do any good. Right? You want to factor the entire thing. So if you can't factor the entire thing, then usually the rule of thumb is leave it in totally expanded form, not just factoring a part of it. So it's better to leave this, to put it in that form. All right, so let's try this thing. So here is one of those upside down hyperbolic cosines that are forming these beautiful arches that are self-supporting. Strongest shape. And we want to find the volume of this kiln. So our concept is, find the area of the face multiplied by 6. That's going to be the volume. To find the area of the face, we would need to be able to integrate this function from this left endpoint over to this right endpoint, or we could integrate from 0 over to that right endpoint and then multiply by 2 to get the area of the face. Make sense? So this is going to be a little abstract, but let's go for it. Let's figure out what this point is right there. So if we want to know what that point is right there, we are setting 3 minus cosh of x equal to 0. So this will be cosh of x is equal to 3. And then we would have to solve for x. We obviously don't know an x value whose cosh is 3. So the only thing we could do here is write this as inverse cosh of 3. That's all we could do. So our integral is going to be for the area. Let's just do the area of the face for a moment. The integral is going to be 2 multiplied by the integral from 0 to inverse cosh of 3 of, we're integrating the curve, 3 minus cosh of x dx. So that would be the area of the face. So this would be 2 multiplied by 3x minus sinh, integral of cosh of sinh, from 0 to cosh inverse of 3. Plugging in 0 gives no area. 3 times 0 is 0. Sinh of 3, because sinh looks like that cubic function, it goes right through the origin, so sinh of 0 is 0. So here is our area. 2 multiplied by 3 cosh inverse of 3 minus sinh of cosh inverse of 3. And that's the exact form of the area. We don't know a way to evaluate this. If it says to approximate, we would have to type it into a calculator or into Desmos to approximate it. Therefore, the volume will be the area of the face multiplied by 6. So we're just going to type, if we want the volume approximated, we're just going to type this right into your calculator, right into Desmos. And that would give us an approximation. So that'll be our volume. And if they gave us units, we would put units on there. I don't think they did. So there's our volume.
Are you able to do cosh on a scientific calculator?
Yeah, most scientific calculators will have a catalog, and you can scroll through the catalog to get to that function. Most of the calculators will have some way to get to all the weird functions that aren't on the keyboard. Like in Desmos, Desmos will act the way you think it would act. So we could just do, whoops, what happened there? Minimize that. It's like in here, we could go 12 and then 3. It should recognize cosh inverse. Just get up there. Cosh inverse of 3.
How did that 2 become a 12?
Because we multiply by 6 to get from area to volume. So that's 6.
Okay, and that was the distance.
Yeah, that's the distance, the depth of it. So, and then in here we could go minus sinh of, yeah, it sounds like Greek. Cosh 3. So that would be it's the only way to do it is to get some sort of graphing, some sort of technology. So that would be our approximation. All right, any questions on any of that?
We wouldn't need that final number for the exam.
No.
Okay.
Yeah, no. We're just going to focus on derivatives and integrals. That's going to be the gist. Okay, so let's do a tiny bit of review type stuff. So the pumping problems, not super hard, but you've got to practice them. So let's do another pumping problem. Let's suppose we've got the inverted cone scenario. And let's suppose that we are going to pump the water out the top. Let's suppose that we're pumping it out. Let's suppose that's 3 meters. Let's suppose this is 10 meters. And let's suppose that this radius up here is 2 meters. So we have that. And so we want to find the work in pumping all that water out the tank with that 3 meter pipe at the top. So first tell me, what is the acronym that we're going to use to find this work? So add volume. So ADD volume. That's going to be our acronym. We're dealing with Earth, so our acceleration due to gravity is 9.8. We are dealing with water, so the density is 1,000. How about limits of integration? So the tank is filled. That conical tank is filled.
0 to 10.
0 to 10. So we have a cross-section of water for all those y values between 0 and 10. The pipe has nothing to do with the limits of integration. The pipe only is going to matter with our second D. Let's draw a representative cross-section here. So there's our representative cross-section. That's at a height of y. So there's our representative cross-section at y. How far does this representative cross-section at y, how far does it have to travel to get out of the system?
10 minus y.
13 minus 13.
13 minus y.
Yeah.
13 minus y. So this is where that pipe part comes into play. If we're just pumping it right over the lip, it would be 10 minus y. But that cross-section right there has to travel this far. This whole thing is 13. This piece right here is y. So this piece is 13 minus y. Y is the height of that cross-section. 13 is the total distance. So that complementary distance is 13 minus y. That is our second D. Now let's find the volume. Volume is the cross-sectional area multiplied by dy. So as soon as we add this thickness here of dy, now we have gone from a cross-section to a slice. So a slice has some thickness to it. So we need the area of this circle multiplied by dy. That's the volume of the slice. In order to get the area of the circle, we need the radius. In order to find the radius, we need the equation of that line. So we need to build a coordinate system here. This point, of course, is the origin. How about that point right there? 2, 10? Everyone agree? 2, 10. This line then is y equals mx. No y-intercept, or the y-intercept is 0. Slope, we go up 10 over 2, so the slope's 5. But we have to solve for x. So x is y fifths. Do we need to double that for any reason? When you find the area of a circle,
It's a radius.
all you need is the radius, right? It's not like the width of that trapezoid thing where you had to double it to get all the way across. When you find the area of a circle, it's literally just halfway across that matters. So that's going to be pi multiplied by the radius squared. So the radius squared will be that. That's the area. And now if we multiply by dy, that becomes the volume of our slice. So we should end up with 9,800 divided by 25. And there's a pi in the numerator. And this will all be 0 to 10. And the only thing that's left is going to be 13y squared minus y cubed. So any issue to that moment? All right, we'll stop there. I'll finish writing it up as soon as you guys are gone. I'll write it up and finish it off. But the most important thing is that you understand up to that point. So ADD volume for work, ADD area for force. Main things. All right, well, I'll be available till tomorrow afternoon, so I'll be checking email, doing all the things, grading your worksheets tomorrow morning. And then I'll be back Tuesday. I can answer emails on Tuesday as well before.
You gonna be in the Mass Center on Wednesday?
I am gonna be in the Mass Center on Wednesday, yes. Yep, I will be in the Mass Center on Wednesday. So hopefully there's plenty of opportunity. Sunday and Monday are out though.
What time on
Let's
Wednesday?
Say again?
What time on Wednesday?
I am in the Mass Center from 9 to 11 on Wednesday. 9 to 11.
Sweet.
Yep. Yeah, I'll stay. Yep, I stay. As long as you need me to stay, I'll stay. We can do math. If 2 hours and 15 minutes isn't enough, stay. We can do more.
What?
Sure.
About the notebook, actually.
Absolutely.
Saying I no longer have permission to access them?
So that's sometimes the
I saw you.
If I know the formulas.
Yeah.
As far as I can tell, it's still letting me like.
yeah. Usually that's a syncing issue.
Once you understand the concepts, then it's like, it's just fun. Like,
You are
it makes sense.
connected to
It's,
Wi-Fi right now?
memorization is where I
Let's
kind of.
try this. If we right click on there and click sync notebook now, that sometimes will clear that up. And like you said, usually it doesn't actually matter. If we can clear it up with that, that would be ideal. So you are still able to come down into here and fiddle around. Same thing then.
1 and 2.
Interesting that it's doing that.
No matter how hard I can't get the last two on 6.2.
Oh, and 6.2.
My guess is
I
that
don't know what
the
I'm doing wrong.
signal is not great.
Yeah.
Maybe
Yeah,
it's
no, I
small,
get it.
right?
me insane, 'cause
My guess is that
I-
it's gonna
I
be
go through all my
meaningless,
math and I
like when you
don't
get to.
see any problems.
Your
But I
home
don't
Wi-Fi.
Yes.
Maybe in the hall though, just right click on there and just see if it will sync when
It was like,
the signal out there. is
do
bad.
it the washer
Yeah.
and the disc.
Yeah, if you go out there and do it in the main hallway,
Show me.
if not in a huge hurry, come back and tell me if it works.
You got this my answers? Okay.
All right, questions?
Yeah, that's my question.
Sure. Oh, let me get the pause on that recording.
You should get the same volume.
Right. Theoretically, yeah.
So that means